So in this video, we want to look at the derivatives of some special functions that we haven't really touched on yet. So like some of those common functions that come up a lot, but they don't fall neatly into the power rule, and they're difficult to derive via the definition of the limit. So first of all, the trig functions. Okay, so these ones I just want to present without proof because, again, we're not really going to spend a whole lot of time on trig. It's mostly just good for examples. So they will come up in some examples. So it's good to play around with these, but to prove them, they're really using rules that we kind of skipped over in Math Tools 1. So here we can see the derivative of sine of x is cosine of x. So this is maybe something that we could easily see from the graph. If we change this one to sine of x here, you can see the red line here is sine of x, and the blue line is the derivative of that, which is cosine of x, right? So if you recognize cosine of x is just sine of x moved over a little bit, and that's exactly what we have here. So the other way, the derivative of cosine of x is equal to negative sine of x. Okay. So again, these ones, you can prove these. They just use some additional formulas that we didn't cover, namely like the sum of two angle formulas. So they're not too difficult if you want to go ahead and try those looking up some of those formulas. But we'll skip the proofs of those here. So if again, I'm not really, I would like to use trig as examples, but won't really emphasize it too much. So if you ever need the trig ones, anything to do with trig, like trig values or the derivatives of the trig functions, I will provide them in the problem. Okay. So next, a really important one here, the derivative of a power function, a. So this is going to be equal to a to the x times the natural log of a, if a is greater than 1. Or better yet, if a is greater than 0 and a is not equal to 1. Okay. So the this one in general, it is important, but the more important version of this is the e to the x. Okay, specifically e to the x. So this implies that the derivative of e to the x is e to the x times natural log of e. Natural log of e is just 1. So this is equal to e to the x. So in other words, e to the x is its own derivative. Okay, this is actually, this is why e is so important, is because it's precisely the value that is its own derivative. Okay, so all exponential functions are proportional to their derivative. In other words, their derivative is the same function times some constant, natural log of a. E to the x is the exact point where it's identical to its derivative. Okay, so that's a very special property. So the proof of this one, it's again, I'll just kind of go over the sketch of it. It's a little bit, I want to say, like recursive. So what I mean by that, let's just look at it. Let's look at e to the x specifically. So the limit of h as h goes to 0 of e to the x plus h minus e to the x over h. So we'll use the exponent properties to rewrite this as e to the x times e to the h minus e to the x over h. Okay, so this is the limit as h approaches 0 of e to the x times e to the h minus 1 all over h. Now, e to the x has nothing to do with this limit, right? We're looking at the limit as h approaches 0. So we can pull that out. In other words, it's kind of like a constant at this point because it's, the limit is about h. This has no h in it, and it's just being multiplied, so we can go ahead and take that out. In other words, the limit as h approaches 0 of e to the x is e to the x, so we just take it out. So e to the h minus 1 over h. So this part in particular, notice that 1 is e to the 0. So we could rewrite this as e to the x times the, trying to think of how we would maybe write this, d. Okay, so over here, this is e to the h minus e to the 0 over h minus 0, right? So this is the derivative of e to the x at 0. So this is like d dx of e to the x. I guess we'd write it like this. In other words, if f of x equals e to the x, then this is like e to the x times f prime of 0. So this isn't a good form of the derivative, but what it does is it simplifies this down to just finding the limit at this point, which is a little bit easier to do. So you can, the general process of this then is to approximate this point via the graph or via a table. And then you'll see that this point right here is 1. And then this is just 1 times e to the x. So then you just have the e to the x part. Okay. So that's why I just meant that this is like a sketch of the proof. Okay. So you get the e to the x part by itself and then show that all you need to do is find the derivative of e at 0. And then you go ahead and approximate that and show that it's 1. Okay. So the important part is, of course, what it is, not the proof. But I just wanted to kind of show the general idea of where this comes from. Okay, so then naturally, we also are going to want the derivative of a logarithm. And we almost always look at the derivative of the natural logarithm. I mean, I don't even remember the last time I looked at the derivative of a different logarithm. So the derivative of the natural logarithm is 1 over x. Okay. And we can prove this one. So the proof here. So we'll let y be equal to the natural log of x. Okay, and of course with this, x has to be greater than 0. Then this implies, I'm actually realizing as I'm writing this that this does use implicit differentiation, which we haven't gotten to yet. But I'll just show it anyway, and then we'll go over again what it means when we get to that chapter. Anyway, this means that e to the y is equal to x. So then you take the derivative of both sides here with respect to x still. So this is where the implicit differentiation comes in. And I won't get into it here. We'll look at a different video on it. But essentially when you're, you don't have just y by itself here, but you're taking the derivative with respect to a different variable, what you get is this right here. Okay. And then the bright side is still equal to 1. And then this is going to imply that dy of dx equals 1 over e to the y. Okay. And 1 over e to the y is the same thing as 1 over x because of this part right here. So we'll revisit that when we get to the implicit differentiation chapter. But this is the idea right here. So this is for the natural logarithm. If we do have a regular logarithm, or I should say a logarithm with a different base. So say log base b of x, then the derivative is 1 over x. There's different ways to write it. We could say 1 over x in the denominator times the natural log of b. Okay. So again, it's proportional to 1 over x. You just multiply by this extra constant, natural log of b. And if your base is e, the natural log of e is just 1, so it just becomes 1 over x.